All right, great. Thank you so much, Harsha. This is Mudit Saxena. And Greg, do I have control of your screen?
I just passed over control. It's waiting for you to accept it. It says you're controlling right now.
Says I'm controlling. Yeah, I think we're good. Okay, thank you very much. All right, Greg. Thank you, Harsha, for that introduction. And Greg, thank you for this opportunity to speak to all of you at CABA today. This is not just an opportunity for us to speak to you, but also an opportunity for us to listen and learn from you about the type of questions you may have about automated shadings. And then we can take that back to our group that's working on the white paper and hopefully incorporate that into our white paper. So on behalf of that entire group, I'd like to thank you for this opportunity too. So when CABA approached us to work on this white paper on automated shades, one thing that we pretty quickly got around to discussing and agreeing upon was we need to start this white paper with answering the question of why. Why do we care about automated shades? Why is it important? Why should anyone pay attention? So this morning, I'm going to talk to you about the why question. Following me will be Justin talking more about the how of how automated shades have developed over time and have sort of changed the way we look at things and look at our buildings and windows. And then finally followed by John, who's going to talk a little bit about who is it that really works to help make these buildings automated and with automated shades. So with that, I'll get started with my slides and presentation. Greg, I think you might have to take control back. It seems to not be working. Could you? Yes, thank you very much. All right, so I'd like to start here. And my first argument is that we spend over 80% of our lives inside buildings. That's a very big number. That's a lot of our lives that are spent inside of buildings. So it's important that we design the indoor environment well and to be conducive for occupant health and well-being. And so we must strive to make these buildings as healthy and as comfortable as possible. Next slide, please. Now, windows are an essential element of that indoor experience. Windows obviously create that link to the outside world through views, and that's a very important part of why we have windows in the building in the first place. But research recently has pointed to the fact that the exposure of occupants to full spectrum daylight really kickstarts our internal circadian cycles. And very recent research has linked this directly with daylight. And so it's very important that we get that dose of daylight. And if our buildings don't provide that, that can lead to potentially unhealthy situations where people are complaining about things that relate to headaches and low immunity, stress. All these are linked to your circadian cycles, and so it's important. It's very important that we provide that daylight to the indoor environment, and so that's where windows really come in. Next slide, please. So windows are important, but designing good windows can be very, very challenging. And anytime you put a hole in a wall, you're going to have heat, glare, and light come in from that. And you have to really design for that. And it's very challenging because heat, light, and glare from a window will change over multiple times over the course of a single day. It changes by shading, by reflection of other objects that are on the outside. So while some of it is predictable, a lot of it is unpredictable. And so as architects, we really have a tough time with this. And it's very hard for architects and designers to really build buildings and windows that can really create that optimal environment we're looking for on the inside, from a thermal comfort, from a visual comfort, from a daylighting perspective. And as architects, a lot of times we just kind of think of it and we don't think too much about it, and we hope that the window that we're providing is not going to have any problems. Next slide, please. But in reality, windows do create a lot of different kinds of problems. And here I've brought a couple of examples here. So on the left, bottom left are a pair of pictures that I took at a Macy's, and they had this big skylight above them. And over a couple of, within an hour, you can see how the glare situation changed on that monitor, rendering it almost useless. And the person who was behind the counter was complaining about this, and he was saying that, well, yeah, this happens about 3 hours every day, and then it only happens in the winters, and then in the summers it gets better. So I was kind of like, okay, that makes sense. But it's really important that we understand that whenever we put a hole in a wall or a roof, it's going to start to create these issues. The second pair of pictures on the right are a classroom, and this is in downtown San Francisco. I was attending this, and we were talking about daylighting, of all things. And within about 10 minutes, suddenly we had these streaks of light that started to show up from the window, and it was causing a lot of problem for the students in the front of the classroom. And we wondered where this came from, and it was actually reflected off of the glazed facade next to the building. And this is very interesting because this is sort of what I'm talking about, the unpredictability of it. There's so much you can say from predicting the way the sun moves around, but then it's really hard to predict when things will be glary. And so my question is, are we really asking too much from a simple window? A window is a static solution to what is essentially a dynamic problem. The sun being the dynamic element, it keeps moving around all the time, and the window is a static solution. So what can we do about that, right? So over time, what we've done is we've said, well, how about we provide some manual blinds and shades to this? Next slide, please. So our solution has been manual blinds and shades. And so what's wrong with manual blinds and shades, you may ask? Next slide. Well, if this picture is any cue as to where I'm going, you'll be able to answer it. Well, there's a lot that's wrong with manual blinds and shades. Occupants occupants are not the best people to optimize the way blinds and shades are operated or deployed. Next slide, please. And recent studies have shown that they really are not very engaged with optimizing the indoor environment of their space with blinds and shades. A study from University of Oregon 2017 looked at a bunch of buildings in downtown Boise, and they concluded that about 51% of occupants did not change their window shades position even once, and 20% just adjust their shades once or so annually. So combine that, that's about 70% of people who are really just touching their shades once in a while. So clearly occupants are not really the people who should be entrusted with creating the most optimal solution for thermal and visual comfort inside their spaces. But that's what we have with manual shades. We provide these manual shades so that occupants can counter the most extreme conditions, but they are not really the best to create or operate these shades efficiently. Next slide, please. And so this is where automated shades come in. So there's a lot of benefits of automated shades, and we'll talk a little bit more about that. But a couple of benefits that we want to highlight is, one is energy benefits. More predictable indoor illuminance will lead to better managed daylight. It removes the uncertainty that comes from having controls given to occupants. And studies have shown over 37% increase in lighting energy savings. It's one of our studies that showed that. The better occupant comfort, because you have a lot more control over exposure to sun, and better management of window heat exchange, again, leads to HVAC savings. So I think it's pretty easy to imagine why the case can be made that automated shades lead to more energy efficient buildings, and that's true. Next slide, please. But the bigger benefit, in our opinion, is really the productivity benefits. And there are studies, there's two that I highlight here, about student performance increasing by 7 to 20% in glare-free daylit classrooms, and office worker productivity increasing by 6 to 12% when they have better access to views and windows. And there are other studies that have been put forth that also give the same message: is that better access to windows, less glare, and more daylight increases productivity. So on the bottom of the slide is this rule called the 330-300 rule, which is very interesting. It says that for every square foot of real estate, commercial real estate, the owner of that building is spending $3 on utilities, $30 on rent, and $300 on employee salary and benefits. That's $300. The biggest chunk is that. So with energy savings, you can reduce that $3. But with productivity benefits, you're really attacking that 300. So even a 10% increase in productivity can more than make up for the rent of that space. So you can see that how if productivity benefits can really dwarf all the other benefits. And clearly there are benefits to automated shades in improving productivity of occupants. So with that, I'll conclude the why section, and hopefully we've made the case about why automated shades are important and why you should be looking at them. I'll hand it off to Justin next to talk about the how. Justin, we can't hear you.
Unmuted. Can everybody hear me?
Yep, I can hear you now.
Hi, I'm Justin Francilla. As you saw by my bio, I've had a considerable amount of time in the industry. And I have found that there is a lack of understanding, a general misunderstanding of the benefits of especially more high performance windows in terms of, as Mudit said, managing daylight and generally managing heat and generally providing access to daylight, something that some types of window commonly found in generic buildings do not provide. As a result, where we've come from and where we're going is that we went from situations whereby the original motorization that was available was designed to operate a patio awning, and that was about it. We've evolved considerably to creating a situation where the motor facilitates the management of the window covering, and then there's all kinds of ancillary benefits, which Mudit has alluded to. Next slide, Greg. In the early years, as I mentioned, there was an effort to provide convenience. The convenience of operating primarily an awning or some kind of rolling shutter system, some kind of security shutter that was used primarily in Europe, and it was one switch per motor and nothing else. So, and then it wasn't even possible to have a remote control in the early days. It was just a switch on the wall and a very cumbersome, ugly-looking switch, and it would allow the motor to push the awning out and bring the awning in, and that was it. And it was line voltage motors only, and we all know that line voltage can cost a lot in terms of infrastructure costs. The concept of automation really didn't exist, and motorization was cumbersome and costly. And as we moved along, originally, if you wanted numerous window coverings and or other types of solar protection to be operated, you'd have a series of switches on the wall, which would all be working independently. So if you wanted something to work as a group sort of scenario, you would have to, literally flick 4, 6, 10 switches, which would be unacceptable and from a design point of view, very, very unattractive. The motors were noisy. You couldn't really have them inside because they sound like a train going through the building, and integration, like I said, was not possible. And that continued for many, many years until not long before I entered the industry, which was in 1998, which tells you, as everything else was moving along effectively, the industry, the window covering industry, was lagging behind in terms of technology. But there's been a massive very exponential growth in the technology since then, and certainly in the last 2 decades it's changed radically. However, just the picture on the bottom right indicates that what's something that was happening a lot as technology evolved. And it's what we call wall acne. You have all these different switches controlling different items, and or different devices, I should say. And it's, again, very unattractive. And this is not an uncommon scenario that I have seen throughout my 21 years at Somfy. One will control lighting, another one will control HVAC, another one will control motors, et cetera, et cetera. And this, because of a lack of understanding of the technology, this is considered acceptable, when in fact, most people will tell you that it isn't. So next slide, please. So technology today has taken the concept a lot further. We still have room to grow, a lot of room to grow, but costs have come down considerably and are much less complex. The systems, I should say, are much less complex. The systems can be controlled in any configuration now. There is no need to worry about having multiple switches on a wall. Any group control or individual control or device control is readily possible. The motors are available in a number of different options, and they include line voltage motors, low voltage motors, battery motors, solar powered motors, and even what we call power over Ethernet, where you're using communication cable Cat5 to power the motors and provide communication. That technology is at a somewhat elementary stage right now and will certainly improve. Eventually, we'll probably have trickle charge batteries embedded in the motors, and they'll be essentially self-powering. And we'll talk a little bit about that in a second. The motors are virtually silent. For the most part, they are silent, and that's important when you have where an elevation may have 20 shades on it and then numerous motors. You may be able to power an elevation with 20 motors or 20 shades with 5 motors, so it would be motor. And that's another misunderstanding, which adds to cost. I've been in many buildings where every individual window shade or blind is controlled by one single motor. That was what was assumed, and that's what was sold. That is, in fact, not the case, and one of the problems with increasing infrastructure costs. And infrastructure costs are one of the big impediments to moving forward in this concept. It is assumed by many people, and it is also applied by many overzealous people who are trying to sell you a product rather than a concept. And as a result, you are ending up with costs that are taking the budget or moving excessively outside the budget that's provided. But anyways, as far as controls are concerned, you can have computer control, you can have app control. It is indeed the Internet of Things that involves automated shading. So we've come into this new realm, maybe slower than other elements have, but it is very much becoming the Internet of Things in the window automation sector. Next slide. I mentioned power over Ethernet. Again, infrastructure costs involving both line voltage and low voltage motors in the fashion that we do use low voltage cable for low voltage motors does cause a lot of problems as far as infrastructure costs. We have moved towards the concept of using Cat5 and Cat6 cable to power motors, but eventually we will have embedded power over Ethernet motors, which will allow you to connect to a cable such as the one on the top right, which is a Cat5 cable, and just plug it into a series of devices which will provide power to those motors. The same concept is being used in lighting very heavily, among other components in a space. There are still some caveats to this technology, in that some of the components have excessive wattage, and once they come up with the concept of OLED lighting, OLED lighting, the lighting business will exponentially jump to power over Ethernet, as will be the case with motors that are integrated that way. And we will no longer have to use traditional line voltage cable, which is what's shown on the bottom right, such as MC cable in some jurisdictions. such as Los Angeles and New York and Chicago, you have to put the cable and conduit. And having worked at an electrical wholesaler at one time, I know how expensive that can be. And once again, you're breaking the budget, maybe not because of the technology, but because of the infrastructure costs alone. So as we move forward, they will be significantly lowered and the concept will become much more accessible. And of course, less componentry will be involved, less parts and pieces. It'll be more seamless across the board. And much of that has happened already, but is going to continue to progress over the next couple of years. And it's not going to be too far down the road where we may very well have self-powered motors, which have a battery contained within the motor itself, which will be trickle charged, and you can just leave it alone. Of course, solar-powered motors will become much more popular. Right now, the technology is somewhat basic, and it will become much improved in the years to come, where you'll just plug into a solar array and you'll be off to the races. So, next slide, please. One of the things that's plagued the industry significantly, and something I have recognized to be a real problem, is with the myriad of solutions that are out there, the question comes up how to specify, and how does a specifier, no matter whether it's a general contractor, even if it's a building owner or a property management company, whatever the stakeholders are, let alone architects and designers, they get a lot of information thrown at them. And as a result, it's very difficult for them to disseminate what is right, what is wrong, what is the appropriate solution, how does it apply to the project, and how does it apply to the budget. So the critical things to address are, what is the objective? If you're simply looking to move the shade up and down, and in many cases, in most cases, that's all that needs to be done, is move the shade down when there is direct solar glare and direct solar gain and direct glare, and move it up when the sun is above you. There is no need for greater complexity, greater components, and greater cost for most examples. Now, you got to ask yourself, where is the project located? And if the project is located in a building core, for example, you may have reflected glare, as Mudit pointed out, from an adjacent building. You may have conditions, you may have reflected heat from an adjacent building. If there's a big glass building in front of you, that's going to create a problem. And in those particular applications, a more sophisticated solution is required and is recommended. But the thing that I like to make people be aware of is that that is not the standard. It's not what you see in most of the buildings in the country. And yet what happens often is a one-size-fits-all solution is applied to all buildings. It can be maybe too basic a solution, or it can be a overblown solution. Too often, the standard is perceived that the solution needs to be many hundreds of thousands of dollars, very expensive, and it's basically written off, and what we end up with is a VE situation where we get nothing at all. So as far as how the system is to be operated, whether it's standalone or it's to be integrated, is it to be controlled by a lighting control system, or whether it's going to be part of a overall home automation system, such as you'll find in a home automation system where it controls every component in the building. But there's professionals out there that are objective, that can tell you what it is that they recommend, or they can obviously recommend something, but they can tell you what you actually need that's going to be effective and provide the appropriate solution within your budget. So the last thing I want to point out, what is the budget? Well, that has to be established. What happens in too many buildings is there really is no budget for window coverings. It's an afterthought. Most architects have far too little time to worry about this subject, and as I like to say, they're more interested in more concerned with poured concrete, making sure that the building stays up, which is appropriate, of course. Many architects have told me that, but the reality is that there needs to be a budget established for window coverings, automated window coverings, and even if that is decided to be, that budget is decided to be reduced, or if that concept is decided to be eliminated, It's better to do that at the outset rather than have no solution at all and trying to put a Band-Aid on the problem and then having to bring people in to fix the problem after the fact, which can be much more costly than originally expected. So that's my my sense of the situation. I hope it's helpful. I'll pass it over to John.
Good morning, this is John. Can you hear me clearly?
Yeah, we can hear you.
Okay, great. Well, it's a privilege to present with Mudit and Justin, and it's also a privilege to be able to address your group today. You can go ahead and go to the first slide, Greg. I'd like to propose two thoughts or ideas when planning any shading project, automated or manual, although automation is always the best control option for all the reasons you've just heard. The first would be to rely on computer simulations to help the team select the most efficient glass and shading combination. These simulations are extremely useful for identifying problems, not only at the conceptual stage, but for buildings that already exist, and for identifying what glass and shade combinations are going to be the most efficient and effective working together. And the second idea would be to always have people on the team who understand the physics and dynamics that are taking place between the glass in the building and the shades behind the glass. It's been discussed. Typically, there's far more planning and discussions about the motors and automation system that control the motors, and certainly that's very important, but more often than not, there is not enough thought that goes into the material selection aside from cosmetics. It's usually form over function. And I'll give you some examples of why better planning is so important. Next slide, please. You see the reference to the term Trome wall under the picture to the left, and I just want to tell you quickly what a Trome wall is. It's an architectural feature that's used when building passive solar homes, usually in cold climates, and they are very effective in collecting solar energy to heat a building. In effect, they use the greenhouse phenomenon where glass is transparent to light energy, but opaque to heat energy. It's like a gate that only opens one way. All the sunlight that comes through the glass is absorbed on a dark surface, it's converted to heat, and the glass won't let it out. It's trapped, and it just keeps building on itself. Excuse me. Now, you'd think because I live in Phoenix, Arizona, that I don't see many Trome walls, but I see them every day, all the time. And if you look around, you see them too, wherever you are. And these are unintentional Trome walls that are built by people who do not understand what happens when they specify dark materials behind glass. It causes increased HVAC and lighting expenditures, and it's extremely uncomfortable for those people who work directly adjacent to the windows. The second picture, excuse me, is from a 2012 New York Times article, and this is about the Sandra Day O'Connor Federal Courthouse, and it's right here in downtown Phoenix. It's just one of many articles that's written about this building. You can look them up, they're interesting. And although the title of the article speaks for itself, they cannot cool this building down in the summer. Although it's not an example of a Trome wall, it is an example of not recognizing the significance of the greenhouse effect. And I'm including this because I want to make the point that these errors don't just happen on small projects. They also happen on very high-profile projects like this one that was designed by a very high-profile team. And we've met with the GSA about this building, where the indoor temperatures in the summer are above 90 degrees, far above 90 degrees. And it would be very challenging and costly to resolve this problem after the fact. But the good news is that these type of heat gate issues can be completely eliminated with good planning. Next slide, please. This is a project that Mudit and I worked on together, and although it's not a commercial building, it is a 7,000 square foot home in Beverly Hills, so it costs as much as a commercial building. And the same problems and solutions would certainly apply to a commercial building. We've worked on a number of commercial projects together, and most of them have been at the conceptual stage, and therefore we have non-disclosures, so we can't present them to you. But this homeowner was kind enough to allow us to use their home as an example. They hired us to find a solution to an extreme solar heat gain problem that had been plaguing them since they moved in. It was too hot in the winter, and it was uninhabitable in the summer. And mistakes were made at several different levels on this project. The people designing the building didn't understand the performance values of the glass. They did not consider the glass and the shades as one assembly, and that's important, and I'll address that later. And somehow their mistakes were not picked up by the Title 24 compliance inspection. This is a code, a California code, for some of you may be familiar with if you're in California. And all the wrong performance values were used in the Title 24 calculations because the team did not understand what they meant, and while all of the labeling on the glass indicated that the glass was incorrect, nobody caught it. So as a result, the air conditioning was always running, it couldn't keep up with the load, and the house was just too hot to live in. Next slide, please. So this slide describes in more detail what I said earlier, that we need to consider the glass and the shade as one assembly. They're not two separate things. And the photograph at the upper right-hand corner of the slide shows an end view, as if you were standing looking straight down the window wall. So the shade is unfurled on the left and the glass is on the right. And that's the same image that you see on the left side of the slide with the graphic on top of it. And this graphic is not something that was generated by the computer simulation. It's just there to demonstrate the relationship between the glass and the shade material. So you can see the sun. The red lines coming off the sun obviously show solar radiation, and you see some of it reflecting off of the glass, some of it coming through the glass, reflecting off the shade, back through the glass, and some of it transmitted inside, just as you would expect. And the little squiggly lines represent absorbed heat in the glass and the shade, and then radiating off the glass and shade, and you can see in both directions. But presumably, if it's cooler inside a building, more of that heat is going to move in that direction, because that's just what nature wants to do. So in this case, while the shade material was not the best selection for this project, and it was replaced with a high performance shade, it could have been worse. It was gray in color. So like in the little graphic, it would have been reflecting some of the sun back out through the glass, so at least it wasn't a chrome wall. Next slide, please. So after researching a number of different high performance glass and shade combinations and providing those values to Mudit, he ran computer simulations that considered various glazings by themselves and then working in tandem with different shade materials. And the simulation considers the position of the sun, orientation, shading on each elevation to determine each opening's exposure to direct sunlight. And then it compares all the different combinations of shade and glass assemblies in each opening that would provide the best performance. And the color renderings you see on the right just provide a quick review that identifies the problem windows. Other very specific information like watts per square meter of glass, which is heat, the time and date sunlight heat occurs, which is extremely useful when programming automated shades, and even human comfort. So while in this case, the homeowners were not interested in measuring their performance, based on their comfort, they just wanted to get back in their home, you could see how this measure would be extremely useful applied to the 330-300 rule that Mudit addressed earlier. And this is just one page of a 200+ page report. It's fascinating. I wish I had more time to show you because it really is very interesting. Next slide, please. So in summary, fortunately, all of these problems are avoidable. And in the case of this home, they were all repaired. New efficient glass was installed. High performance shade material was installed on automated shades. And the homeowners are now living in a very comfortable home that performs well. And where you might think that the people who designed this building, who made the mistakes, would not want to hear the mention of our names, they sent us plans for 3 other projects because they said they never wanted to experience this again. So there was a happy ending for everybody involved. So in closing, I would just say that it is not more expensive to use high-performance glass and automated shades if you employ the right people and tools. Going to help you make the right decision. And that concludes our presentation, and thank you for all of your attention.